Voyager 1 is now more than 24 billion kilometers from Earth, farther than any human-made object has ever traveled, and it is still beaming back scientific data from the edge of interstellar space. Let's dive into Voyager 1's crossing into. That fact alone reshapes our sense of scale, but the story behind how a 1977-era probe accomplished this feat reveals the ingenuity of engineers, the daring of mission planners, and the unexpected science that continues to flow from a spacecraft that has outlived its designers. Chapter 1: A Bold Idea in the Cold War. In 1977, amid Cold War rivalry, NASA launched two identical spacecraft, Voyager 1 and Voyager 2, on a grand tour of the outer planets. The mission's original goal was simple on paper: fly past Jupiter and Saturn, capture high-resolution images, and send back data before the probes fell silent. Yet a small team of scientists, led by planetary physicist Carl Sagan, convinced management that the probes could be sent on a longer trajectory, using a rare planetary alignment that occurs once every 176 years. This alignment would allow gravity-assist maneuvers, slingshotting the spacecraft around each giant planet to gain speed without additional fuel. The plan was audacious, essentially turning the solar system itself into a cosmic catapult. Chapter 2: Engineering a Longevity Machine. Voyager's engineers faced a paradox. The spacecraft had to be lightweight enough for launch yet robust enough to survive a 50-year odyssey. The answer was a suite of redundant systems and a power source that would not deplete quickly. Each probe carried 3 radioisotope thermoelectric generators, RTGs, which convert heat from the decay of plutonium-238 into electricity. At launch, the RTGs produced about 470 watts, enough to run the instruments, the communication system, and the famous golden record. Unlike solar panels, RTGs work far from the Sun, ensuring continuous power as the probes recede beyond the orbit of Pluto. The onboard computer, a 8-bit processor with 69,000 instructions per program, seems primitive by today's standards, yet it could autonomously execute complex sequences, pointing the antenna, adjusting course, and protecting the instrument suite from radiation spikes. Redundancy was baked into every critical component. For example, there are multiple thrusters for attitude control, and each sensor has a backup. This foresight is why Voyager 1 can still function after 4 decades of exposure to extreme temperature swings, micrometeoroid impacts, and intense radiation belts. Chapter 3: The Grand Tour and the Gravity Assists. Voyager 1's first major milestone came in March 1979, when it swung past Jupiter at a speed of 47 km per second relative to the planet. The probe captured the first close-up images of the Great Red Spot, discovered active volcanism on Io, and revealed Jupiter's faint ring system. Using Jupiter's gravity, Voyager gained a boost of about 9 km per second, propelling it toward Saturn. In November 1980, the spacecraft performed its second gravity assist at Saturn, skimming past the planet at 35 km per second. This maneuver not only sharpened its trajectory toward the outer solar system but also sent Voyager on a path that would eventually miss the other giant planets, an intentional decision to prioritize speed over additional flybys. The gravity assists reduced the travel time to the heliopause, the boundary where the solar wind's influence wanes, to just over 35 years, a feat that would have been impossible with conventional propulsion. Chapter 4: Crossing the Heliosphere. The heliosphere is a bubble of charged particles blown outward by the Sun, extending roughly 120 astronomical units, AU, from the Sun. Inside this bubble, the solar wind dominates. Outside, the interstellar medium, a tenuous mix of plasma, dust, and cosmic rays, takes over. For decades, scientists debated where the heliosphere ends and what lies beyond. Voyager 1 carried a plasma wave instrument capable of detecting electron density, a proxy for the surrounding environment. On August 25, 2012, the instrument recorded a sudden, sustained jump in electron density, matching the values typical of interstellar space. Simultaneously, the probe's magnetometer measured a change in magnetic field direction, and its cosmic ray detector noted a sharp rise in high-energy particles from beyond the Sun. These three independent signatures convinced the scientific community that Voyager 1 had crossed the heliopause, becoming the first human-made object to enter interstellar space. Chapter 5: What Interstellar Space Looks Like. Now, more than a decade after that crossing, Voyager 1 continues to send data about the local interstellar medium, LISM. One key discovery is that the LISM is not uniform. It contains dense clumps of plasma interspersed with more rarefied regions. The probe's measurements of cosmic ray flux have helped refine models of how galactic radiation propagates through space, which is essential for planning future crewed missions beyond the protective bubble of the heliosphere. Another surprising finding is the presence of a magnetic wall just beyond the heliopause, an abrupt increase in magnetic field strength that appears to act as a barrier, slowing the inflow of interstellar particles. This wall could influence how the Sun's magnetic field interacts with the galaxy, shaping the shape of the heliosphere itself. Understanding this interaction is crucial because the heliosphere acts as a shield against high-energy cosmic rays that can damage spacecraft electronics and pose health risks to astronauts. Chapter 6: The Golden Record, a time capsule for the cosmos. While the science instruments dominate the narrative, Voyager also carries a cultural artifact, the Golden Record. A 12-inch gold-plated copper disc, it contains 115 images, 90 minutes of music, and spoken greetings in 55 languages. The record was curated by a committee led by Carl Sagan and was intended as a message to any extraterrestrial intelligence that might encounter the probe. No alien has yet responded, but the record serves a deeper purpose. It reminds us that exploration is not only about data, it is also about humanity's desire to be known. The very act of encoding our civilization onto a metal disk and launching it into the void reflects a profound optimism about our place in the universe. Chapter 7: The Human Element, Decisions that Kept Voyager Alive. Voyager's continued operation is not automatic. It requires constant monitoring and occasional software updates sent from Earth. In 2017, engineers discovered that one of the spacecraft's 3 RTGs was producing less power than expected due to a subtle degradation of its thermocouples. Rather than shut down non-essential instruments, the team reprogrammed the onboard computer to prioritize the most scientifically valuable sensors, extending the mission's life by another few years. A more dramatic moment occurred in 2020 when a software glitch caused the spacecraft to lose lock on Earth's deep space network. Engineers on the ground performed a series of reset commands, essentially rebooting Voyager's computer mid-flight. The maneuver succeeded, and communication was restored, a testament to the foresight of building a system that could be remotely troubleshooted after decades in space. Chapter 8: Why Voyager Matters for Future Exploration. Voyager's success informs several emerging fields. First, its RTG technology demonstrates a reliable power source for missions to the outer planets, where sunlight is too weak for solar panels. Second, the gravity assist technique remains a cornerstone of mission design. Upcoming probes to the icy moons of Jupiter and Saturn will rely on similar maneuvers to conserve fuel. Perhaps most importantly, Voyager provides a baseline of interstellar conditions. As humanity contemplates interstellar precursor missions, such as Breakthrough Starshot's concept of ultralight sails traveling to Alpha Centauri, understanding the density, magnetic field, and radiation environment of the LISM becomes a prerequisite for designing shielding and communication systems. Chapter 9: A Silent Ambassador at the Edge of the Sun's Influence. Voyager 1 will continue to drift farther away, losing about 15 watts of power each year. At its current rate, the transmitter will cease operation around 2025, after which the probe will become a silent ambassador, still moving at roughly 17 kilometers per second relative to the Sun. Even then, its legacy endures, a testament to human curiosity, engineering brilliance, and the willingness to send a piece of ourselves into the unknown. Conclusion: from a Cold War launchpad to an interstellar messenger. Voyager 1's journey began as a planetary reconnaissance mission, but it evolved into humanity's first step beyond the Sun's protective bubble. Its crossing of the heliopause answered a fundamental question: what lies beyond the solar wind's reach? The data it continues to send reshapes our models of the galaxy, informs future spacecraft design, and reminds us that even a modest 8-bit computer can achieve feats once thought impossible. As the probe sails toward the distant stars, it carries not just instruments, but the story of a species that dared to look outward, build a machine that could survive the void, and send a message of our existence across the darkness. The next time you look up at the night sky, remember that somewhere, far beyond the planets you see, Voyager 1 is still listening, still traveling, still telling the tale of Earth to the universe.